Good morning. We're beginning the second day of this workshop. So I'll be the session chair for the two keynote lectures this morning. Our first keynote lecture this morning will be given by Professor OFW19 from Cambridge University. I'll first give a brief introduction to Professor Yasak. Professor Yasak is a professor of continuum physics at the Department of Physics, Cavendish Laboratory, University of Cambridge. He also holds professorship at the University of Zagreb and a fellowship at TU Darmstadt, Germany. And he is one of the two original co-authors of the very first versions of OpenFOAM. And he's also the chair of the OpenFOAM Numerics Technical Committee and a member of OpenFOAM Governance Steering Committee. He is also the founder and managing director of Wiki Limited. Havoya has his first degree from the University of Zagreb and PhD from Imperial College, London. He was a senior development engineer at CD Adapco, which is now Siemens PLM, and technical director at Naval Limited, and he worked on new generation software at ANSYS Fluent. Now let's welcome Professor Yasak to give a year in review for OpenFOAM.
Hello, everyone. Thank you for getting up early in the morning to speak to me, and thank you for being here. As some of you may know, I have two passions in life. One is traveling, and the other one is having lots of friends. So here in Beijing, I'm very honored to be invited to be a keynote on this conference, and I would like to talk to lots of my friends here, with special thanks to Zichen as the organizer of the conference, and our previous organizer for the conference in China, Professor Decheng Wang. So it is my pleasure to be in China again, and thank you for bringing this community together. So what are we going to talk about? Well, first I have some interesting news for you. Today is 2024, and I started working on this code in 1993. Okay, so if that doesn't make you feel old, I don't know what does. Okay, so this is an old code, but it is also a very successful code, and it's not successful because of me, it is successful because of you. So I'm honored to be a part of this community. Traditionally, the talk is year in review, and we are going to go through some of the activities that have been going on, the good ones and the bad ones. And I'm really happy to hear that there is more good things than bad things happening in the world of OpenFOAM. So here is a little overview of the things that I will talk about. Nobody is perfect, and neither am I, but I also like calling out names of people who have contributed. And by doing that, I always forget other people who have also contributed in a significant way. So for those of you that I do not mention, please accept my apologies. But in every area, we need to have one person who is guilty or responsible for everything good and bad that is going on. So we will start with some community and dynamics items, and then talk about the biggest publicly funded effort in the OpenFOAM world, and then carry on with various collaborative developments. In the end, I have a few items of work from my group that I like showing off. I was told that the movies don't work, but we will work on that together and try and figure out how to see some of the pretty animations as well. So let's start from the global picture. So as I said, this is our second time in China in 19 years of organization of this conference. So the next one is the 20th year, and OpenFOAM is no longer a teenager, okay? And neither is the conference. So this is beyond my wildest dreams, and I'm really happy that the community is working so hard. Now, when Miguel presented the conference and various other people in the audience, one of the things that they say is never again, okay? So this is a huge amount of work, and I need to ask you to thank Zichen for his contribution again. So thank you very much for all the hard work that you put in. I'm sure this is a good contribution. Okay, one of the good things about the conference is that it travels around the world. So we have been everywhere, and we like meeting new people and new communities like the one here. Yesterday on the committee meeting, I was told that 70% of attendees come from China, which is really fantastic, meaning that I get to meet a lot of new people. So let's take that in the same spirit forward. On the technical things, last year I have mentioned that there is a new owner of the trademark and copyright of OpenFOAM, and this is a Keysight Technologies Incorporated, where OpenFOAM and OpenCFD have been acquired as a part of the purchase. And every time I hear something like that happen, I go, oh my God, what's going to happen now? And what happened is nothing, which is probably good news. So we remain open source. The trademark is protected from third parties, but we can all use it within the terms of the trademark. And I hope that Keysight Technologies will carry on supporting the OpenFOAM community as ESI and OpenCFD have done before. On a private note, some of you know Dr. Fred Mendonça. Okay, I was hoping that he will be here with us today. Fred, if you're watching, we all miss you very much, and I hope to see you again soon. So, to business. This is an open source project, which means that what we are working on is towards the common good. Some people have been involved in the project for a long time, and I can see lots of them in the audience. And we are all building on the code base experience, validation, benchmarking, improvement of previous generations. So in order to formalize that, we have the OpenFOAM governance initiative, which was started out by Fred, and up until recently it has been managed by ESI and OpenCFD. That needs to be taken over by Keysight Technologies now. And the idea is that the code should be doing what the users are asking for. So there isn't a great overwhelming development line of the things that we would like to use, because 10 years ago nobody knew that cars' batteries will be an important problem, and future brings surprises and the code needs to adapt. The way that we do that is to involve the users and communities in technical committees and special interest groups. Some of them have been long-standing, like automotive applications or turbo machinery. Some of them are new, and I would like to mention Tomislav Maric and the data-driven modeling special interest group. The reason why I'm putting this up is to encourage you to get involved with this for two reasons. The first one is, if you need something new in the code, the best way to push for it is to actually start developing things and looking for collaboration with other people, okay? So that will be the special interest group. The second one is, as you will see on the left-hand side, there is a whole set of things that we should be doing and that contribute to everyone's well-being in terms of OpenFOAM, but they require an immense amount of effort. And because I like mentioning people, I will mention Miguel again, and probably the most successful technical committee, which is the documentation technical committee. All of this is organized by Gavin Tabor, professor at the University of Exeter. And if you would like to know more details about what is going on in various groups, etc., please try and contact him. So recently we had a meeting on the 13th of June, and the idea of these meetings is not to hide and withdraw, but to open up our plans to the community, and that involves not only academic contributors, PhD students, professors, but also commercial organizations like those that are sponsoring this event today. So the best way to improve the software is to get involved with this. So let's just have a quick look at how the community self-organizes. Okay. This started with beer evenings in Germany, where a local group of people in Frankfurt, Stuttgart, Munich, Berlin would come out and have a bunch of presentations in one afternoon and then have a nice meal in the evening. But it has grown to be much more than that. So as good examples of local collaboration, I will mention the Foam Utiliseurs, which is the local French user group, the Iberian user group organizing at A Coruña in 3rd and 4th of October. Miguel, can you remind me, what's the name of the lady who is organizing it? ENCOT, okay. And a few weeks ago, we had the inaugural UK-India OpenFOAM conference organized by Somnath Roy and my friend Shandan Bose from the University of Birmingham. Now that we have survived COVID, we know that we can achieve things without actually traveling to places. So most of these events are hybrid, and you can log in, or in the case of UK-India OpenFOAM conference, I think the entire conference is available on YouTube, so you can actually watch the videos of all the presentations. On my side, some big numbers again, okay? So in 2008, I organized the first summer school. Now we are at number 17, okay? So the summer school is organized for specifically PhD students and young postdocs who are having trouble doing their OpenFOAM work because their supervisors or their local community does not have the expertise to work on the code. So this year we have, I think, 14 attendees coming to Cambridge for 2 weeks to do intensive work on their own projects. So as a part of the summer school, there is always a set of presentations on free surface flows, turbulence modeling, dynamic meshes, C++, programming, basic pressure velocity, etc., depending on interest. But there is always some really optimistic or energetic person trying to develop some new features which then end up as fully blown projects. So the second part of this presentation is about something called the ExaFOAM project. So as you probably know, the earliest lines of OpenFOAM were written in about 1992, and we didn't get any public money for the development of the software all the way until about 2020. Apparently, this is quite typical for large and successful open source projects, because if you can do without, you do without, just to avoid all of the problems with bureaucracy. But in this case, we actually managed to get a big European high-performance computing project, which lasted for 3 years and just finished on the 31st of March 2024. The idea was to push OpenFOAM towards exascale computing. And I was going to spend a lot of time here telling you how this has been achieved and what needed to be done to push this code and actually improve real-life performance on real-life platforms by a factor of 10. You know what's the biggest surprise? It wasn't any of the things that I expected. So People usually speak, make your code run faster, make it be more robust, etc. But maybe 70% of the success of the project was with code usability. And some of the numbers that we have seen within these projects are truly staggering. Okay, so we are talking on running on tens of thousands of CPU with meshes which are so big that parallel decomposition and reconstruction doesn't complete within 24 hours, which is the limit on the amount of time you have on the head node. So it turns out that the code itself, in terms of linear solvers, discretization, mesh analysis, etc., is not really that bad. And there were various things that we could do to the project and to the code in order to make this better, okay? But the real improvements in performance were actually improvements in usability. So here's a little map of all the things that have been done. So the work package 1 was coordination. I'm not particularly interested in that one. The work package 2 was validation and assessment, okay? So we have micro benchmarks, industrial applications, and grand challenges. What does it mean, a grand challenge? Well, some of you in the audience are routinely running meshes of hundreds of millions of cells, but running 2 billion cells is still an order of magnitude more, and it comes with its own challenges. The second thing that we have to do is we have to convince the people who are actually paying for all this that the code can perform and that we have improved performance on the cases that are relevant for these applications. So here in industrial applications, we talk about combustion, marine, external aerodynamics applications, and actually measuring the performance of the code on something that's not a motorbike tutorial or a really big lid-driven cavity, because these are not representative cases. And at the highest level, we have the micro benchmarks. Does the code operate the way you expected? Are the results correct? And those need to be relatively small so that you can repeat them quite often. And now we come to the actual working packages: refactoring, evolutionary, and co-design, profiling, and performance work packages. Okay, so here we can look at the features of the code and find out how to actually make it better. So having programmed this thing for the last 30 years, this has been a really deep learning experience for me. And here are some names and some conclusions that I drew from there, okay? So by far, the most impactful thing that I saw is how supercomputing people do profiling of the code, not on 16 cores, but on 10,000 cores. When you need to find out who is waiting for whom, what communications are locked, is the code actually doing what you think it's doing, and how you can analyze that. The remarkable person who taught me a lot here is Marta from the Barcelona Supercomputing Center. And I realized exactly what it means that I hate parallel debugging. So when Yi Wang makes me do debugging on his case on 100 CPUs, I hate it, but now I know exactly why I hate it as well. Okay, well, it's got to be done, and I always get the dirty work. So the second one was the work from Federico at Politecnico di Milano, and he is a combustion specialist. So what he did is he moved the heavy-duty part of ordinary differential equation solving onto the GPUs, and he made it very successful. Now, when you think about it, it sounds simple, right? So you just take the ODE solution, you move it from one place to another, and suddenly everything runs faster. Well, not that simple, okay? So this has been deployed. The third one is something about parallel mesh formats, data input-output, either natively or within external libraries. So as some of you know, the code got kicked off one of the supercomputing platforms in the USA because at one point it opened 80,000 files for input and output, and the machine just went, okay? So it took a while to get the machine back up. We upset them hard enough in order to be banned from that machine. And a part of the ExaFOAM project deals with this completely mundane issue of data input-output, decomposition and reconstruction that is required to do the work in the right way. And finally, again to my friend Miguel, who looked at algorithmic implications of what we are trying to do. So the basic pressure velocity algorithms that most of people are using come from 1970s. In 1990s, we could do better already, but the difference in performance wasn't completely clear. So what Miguel and his team did is they looked at the various variants of a coupled solver for a very strong nonlinear problem of viscoelastoplastic materials with large deformation and, I guess, free surface, and looking at different levels of coupling based on understanding of physics. So for those who want to know more about the ExaFOAM project itself, please visit the exafoam.eu website and look forward to future releases of this technology that has been developed within the project in the releases of the code. Okay, so one of the things that we did not do within the ExaFOAM project is to consider the use of GPU for CFD, okay? And what I mean by that is to actually move the entire matrix assembly and matrix solution onto the GPU. The main reason I never looked at it before is because I thought it was impossible. But now commercial codes, both Fluent and StarCCM+, have got GPU versions, and they have shown that it is possible, and this is actually working. So the performance gain that you can get without working very hard on it is about a factor of 3. But the insight in the way that this is working needs to be more profound than that. So we need to change the basic data structures and see how this change can work with the machinery of CFD that we are used to. Unstructured, polyhedral, highly parallel, second order, finite volume method, with all the little tweaks that commercial CFD requires. And I have been working with that with my student at the master's course. His name is Sondre Wilsberg, and he's a very scary guy because he's smiling all the time, but his brain is working 3 times faster than I can cope with. Okay, so what he did is he said, if we are going to rewrite the data storage mechanism for matrices, let's find out which one is the best. So I'm hoping that that is going to bring us towards future steps and achieve some of these real performance kicks that will make sure that OpenFOAM stays competitive against the next generation of commercial GPU CFD codes. What about collaborative development? Okay, so there is a whole bunch of people in community trying to do various things. For example, we have the Waves to Foam project that has been successful for quite a long time. We have FireFoam people developing combustion codes. There is a group in Texas working on something called BlastFoam. And one of those is the group of Dr. Philip Cardiff from University College Dublin looking at solid mechanics. Now, please don't get too excited. This is not about linear elasticity and finite elements. There are other codes that can do that, and the finite volume method is not the right way of dealing with that. However, as your problem becomes more and more nonlinear, using the finite volume, quote-unquote, CFD techniques to solve it is becoming more and more interesting as well. Philip and his group have been working on this since about 2000, maybe 2002. And Solids for Foam which is their extension to the libraries, is just doing a new release at the moment. So the kind of things that they are looking at are large deformation, contact, material nonlinearity, geometrical nonlinearity, and fluid-solid interaction coupling. Okay, so if there is time in the end, I will try and show you some of his videos, but just from this, you can have a feeling of the kind of things that they are trying to do. Okay, so the second set of developments which are driven by this collaborative governance structure relates to the OpenFOAM journal. I understand tomorrow we are going to have a more complete presentation on the work that the editorial committee are doing, but I have to tell you that this is one of the most impressive developments in the OpenFOAM environment that I have seen. How so? Well, imagine a perfect journal. It is open, it is free, it is high quality, it does double review, and it makes sure that the data published in your paper is reproducible. I don't think I can imagine one better than that. And today, it's been, what, about 5 years since the journal has been running? I think 4 years, okay? And the numbers are very impressive. More than 30 papers published, 8 editorial board members, 80,000 views, 8,000 followers on LinkedIn, and 2,500 subscribers on YouTube. It is even better than that, because when you publish your paper, we are going to open a forum discussion thread on CFD Online so that people can discuss your work. And some of them, like me, will tell you things, oh, I don't believe you, okay? In which case you have a perfect answer saying, well, the data is there. If you don't believe the results, please reproduce them yourself, okay? But also, you can start building your work from the contribution of the others. I have to say thank you to the editorial board and all the work that you do, and give you my apologies for always missing the meetings. So you will hear more about this journal tomorrow, but now this is not just any old journal. The quality of the journal, the quality of the contributions is so high that we don't want just any paper. We want you to send your best paper to the OpenFOAM journal, because that's where the impact is going to come from. Okay, so probably the earliest working group or special interest group that has started working with OpenFOAM was the Turbomachinery Working Group. There are 2 people here who are responsible for the success, and they are Martin Baudouin and Håkan Nilsson, who both have very strong interest in turbomachinery applications. Well, what's so special about turbomachinery CFD compared to general purpose CFD? Well, you need extensions. There are rotor-stator interfaces, mixing planes, partial overlap, cycling, post-processing tools, etc. But even more importantly, there are validation and verification cases. So porting these around and making sure that the new members of the community can start working with something which is not, well, let's see if the code is working on this set of applications, is the contribution that they are making. Another very successful technical committee is the Turbulence Technical Committee. Well, what's so great about the Turbulence Technical Committee? Number one, they really care. Turbulence modeling in a complicated software like OpenFOAM is problematic because there are multiple models. Doing validation and verification exercises takes really a long time, and being able to prove to yourself and the community that the model is correctly implemented and performs in the way that you would like is not easy. So Timofey and Charlie Mokat have been running this committee for quite a long time, and they not only provide validation, verification, guidance, etc., on what turbulence modeling you should be using for your application, but actually in the code repository there are extensions to standard turbulence model library for specific applications. Here, Timofey is more your RANS kind of person, and Charlie is the LES kind of person. So we have this covered, and their work has been really quite remarkable. Right. So one of the difficult things that we have to do every year is to decide where we are going to go next. And nobody can tell you that, okay? So the conference has traveled everywhere, and as you can imagine, with 19 different places, we are always looking to meet a new community. And here I'm looking at you, the people from China, the people from Asia, the people from Europe, the people from South Africa, the people from North and South America. Please consider if you could be our host in the future. Okay, some years we have very strong competition with multiple people saying, I want to do it next year. But as you can see, the next one is special. The number is 20. We are not teenagers anymore. So if you have the capability, the facilities, and the local OpenFOAM community, please consider organizing one of the future workshops. Right, so a little bit more about my work. And I have picked 3 items here to give you an idea of what's sitting on my desk. So the first one is related to turbomachinery modeling, but it goes beyond that. So in about 2016 to 2018, I had a PhD student in Zagreb who worked on harmonic balance. Okay, so the idea of harmonic balance is that you want to solve a flow which is periodic without solving it in time domain, because if you start up a pump, it needs to rotate quite a large number of times until it gets into the quasi-periodic motion. Okay? With harmonic balance, what we will do is we will decompose our signal for the variable Q into a series of sine and cosine signals and replace the transient signal with a series of Fourier space simulations. The nice thing about it is the way that it has been structured for nonlinear problems is that the transient quasi-periodic problem looks like a series of snapshots, each of which is as complicated as a steady state problem, and they are coupled to each other through the rate of change, DDT term, which is calculated from spectral space. So this has been around for quite a while, but what I found is that there is a difference between the code produced by a PhD student and the code that you can deploy in the community and actually provide validation, verification, and proof of accuracy. So over the last 6 months, I have been rewriting, cleaning up, and we are about to release the harmonic balance method. To give you an idea of the kind of things that it can do, you can take a look at a bunch of pictures of a flow behind an open water propeller, okay? And as I'm increasing the number of harmonics between 1, 2, 4, and 7, more and more details of the fully transient flow behavior will become visible. There is a series of questions. Where is the limit? What do you get with more frequencies? How does that compare to the fully transient solution? What about turbulence? What about rotor-stator interaction, etc.? And this is the work that will be happening over next year or so. So in terms of validation cases, here you can see some comparison for the propeller that I showed you before, showing you the average error that then goes down to very small numbers, like 0.26%, 2.8%, compared to the experimental data. But there is really quite a lot of work here now that the method is actually working properly and converging without too much trouble. There is another set of simulations that I am about to release, and that comes from the University of Zagreb. Okay? Here we are dealing with sediment scour. Okay, so the idea is that you're going to have a channel flow, the river is carrying sand, it is carrying it as a combination of suspension in the volume and little pebbles being driven along the bottom. The code has been developed in collaboration with the German University of Cairo, and every about 3 months I get a question saying, hello, can I please have a copy of this code? And I kept saying no, not because I want to keep the code to myself, but because this animal is really quite complicated and it hasn't been validated well, and it's not one of the standard things that we do in CFD where you can guarantee that the same accuracy will be achieved across a large number of cases. So Tessa took over the group in Zagreb, and she extended and cleaned up this solver, which combines the finite volume method for the three-dimensional transport, the finite area method for the transport along the surface of the seabed, and dynamic mesh deformation or immersed boundary to actually do some of these simulations. Now, this thing is really difficult to validate. So we are still playing with the cases which are beyond the simplest cases that you have. Tessa will present her own results, I think, tomorrow. But here you can see what these simulations look like on micro hydro turbines, which are embedded in the flow of water. And here behind the turbine, you can see the effect of seabed elevation or depression in serial or parallel configuration. Of course, there is experimental data as well. And here's an example for a validation case for scour around the circular pile. Okay, so I decided to release this, but if you jump on it and think this is the coolest thing ever, please expect to have a certain amount of trouble with it. The solver is quite complicated, it is quite fragile, you really need to know what you're doing when you're producing these sets of results. Okay, so the last thing that I wanted to talk about is naval hydrodynamics. Some of you may know that I have been obsessed with naval hydrodynamics simulations since about 2008. In the first versions of naval hydrodynamics CFD with OpenFOAM, I have spoken to a client and they said, oh, this is a very nice code, thank you very much, it is 1,000 times too slow. Okay, so since then, we are 10 times faster than the fastest commercial competitor, but the kind of simulations that we are doing has significantly changed over the last year. In Cambridge 2 years ago, we had a presentation from Dmitry Pankratov doing a project on full-size ships. Okay, well, you know, when we do simulations around cars, we do full-size cars. So what's the problem with doing with full-size ships? Well, there are several. The first one is you don't have any experimental data, because measuring the flow around the ship and measuring the flow around the ship model in a towing tank is a completely different game. So up until about 2-3 years ago, most of the naval hydrodynamic simulations have been done on model scale because this is where we had the data. With the EURES project and the work from Dmitry Pankratov, we started doing full-size ships. Okay, so to give you an idea, a ship will be 300 meters long. Your Reynolds number will be 5, 10 to the 9 or 10 to the 10, dealing with wall functions, surface roughness, and other effects which are related to friction is now significantly complicated. But the good news is that the experimental data is not very good. So you can actually learn a lot from doing CFD simulations on full size. The second issue is that the way you're going to do these experiments is also much more complicated. In a towing tank, you are going to pull the ship at a given speed. You can guarantee that the surface is perfectly flat. Whereas with a full-size ship, you have to run it with propellers, and you have to achieve something called the free sailing point, where the power from the propeller matches the resistance from the ship. Now, there are further problems. If you have a single propeller and it spins like this, and you put your rudder at 0 degrees, your ship doesn't go straight, it turns. Okay? So rather than just having a ship and the propeller, you have to be able to control the rudder and also control the RPM of the propeller and also be able to deal with the waves. So that's my life now. We are going to have a series of maneuvering simulations in calm seas and in waves, where the ship is going to have moving rudders, rotating propellers, propulsion, PID controllers, etc. And you know what's the most interesting thing that I learned here? Suddenly, running your CFD code is much more like an experiment. Okay, so if I want to do a turning circle in waves, I have to find out the RPM. So first you have to run it at calm seas, find out what the free sailing point is, take the RPM. With that RPM, you're going to run a turning circle or a zigzag, etc. And only then do you get to do the comparison with experimental data. So suddenly, my CFD tool looks like the real thing. And that's where the real pleasure of this game comes from. Okay, well, this is all that I prepared for you today. It is time for other people in the community and other people in the conference to make your own contribution. I'm very much looking forward to hearing about the kind of stuff that you want to do, and I want to tell you how very grateful I am to all of you that you have chosen OpenFOAM as the tool that you want to work with. Thank you very much.
Okay, do we have any questions from the audience?
Isn't that just crazy? So the question was something like this. If you want to run on a really big supercomputer, you have to prepare your run, okay? And if I want to run on 20,000 cores, that means that I need to do a domain decomposition of my serial mesh into 20,000 bits, okay? Well, this is not the real CFD run. And on one of the production CPUs, I don't have enough memory in order to do the decomposition. So for these sort of heavy-duty kind of operations that you need to do, they will allow you to run your case on the head node, okay? And these head nodes will have, I don't know, 768 gigabytes of memory, blah, blah, blah. But because the people who are managing your supercomputing platform don't want you to run on the head node, they will arbitrarily limit your CPU time for an interactive run to 24 hours. What's the reason for that? Nothing, okay? It's just the way that it is. But apparently, it is unbelievably difficult to let them do the right thing, right? And what that means is that, I think Sergey will tell us, one of the largest cases that Sergey was trying to do, they couldn't decompose within the 24-hour limit, so they had to change the way that the decomposition is working to get around it. Okay? So there is no real technical problem. They just won't let you run. Okay? And funnily enough, once you do the decomposition, the parallel run will finish in less than 24 hours, and you can use 10, 20, 40, 50,000 cores in order to do these things. I think you will do the presentation on that, right? Already did. Sorry about that.
Okay, we still have time for 1 or 2 questions.
Nobody likes me? I'm off. Thank you again. Thank you.
Oh, right. Sorry, we had we forgot prepared a little gift for you. It's too delicate, so it will take a bit of time to be taken out.
I can try and ask for another question from the audience.
Currently, the dynamic mesh functions in OpenFOAM is quite complex, and for example, there is the offset and also the mesh transforming, and also the rotating mesh. I mean, and all these functions, they distributed in different libraries. I mean, is there any future work to reorganize all these dynamic mesh functions? Do you have any plan to do that?
Okay, well, thank you for that question, because you're really talking about my life now. Okay, so the reason why I wanted to do CFD is because I thought dynamic mesh was so cool. Okay, now we have gone through 4 or 5 generations of different dynamic mesh technologies. The earliest one was mesh deformation, and because this is the simplest one, that one scales properly, but it is not very general. Okay, so we had the mesh motion solvers and various other things. The second one, I almost spent a decade on, which are topological changes. Things like adaptive mesh refinement, layer addition removal, sliding interfaces, etc. And now that I think about it, I think this is a dead alley, okay? Because you can do some things with it, but you don't have the ultimate flexibility, okay?
Yeah, I'm thinking that is it possible to develop a general dynamic mesh method? For example, the offset mesh offset function is most flexible, but it has the disadvantage that the mass conservation cannot be guaranteed. So I mean, maybe some new generation of dynamic mesh maybe should be developed by us. Okay.
Okay, I will tell you a joke, okay? So I know a surgeon, and he's specialist for operations on the foot, okay? And he says for this particular problem, there are 21 different operations that we can do.
Yeah.
What does that mean? He doesn't know what he's doing, because if he knew, there would be only one.
Yes.
Okay, so dynamic mesh is very much like that. Okay, there isn't a general solution to all the problems. Okay, so in these movies that I wanted to show you, for moving rudders in ships,
Yeah.
I use overset mesh.
Yeah.
But if the gap between the rudder and the hull is too small, overset mesh doesn't work. Okay, so I'm afraid that you have to consider the problem that you're looking at and find the best way of dealing with the mesh, rather than using one technique that will work for everybody. And if you invent one that works for everybody, please let me know, because I would love to know as well.
Okay, thank you.
I'm sorry I couldn't answer your question properly.
Okay, thank you.
So this is University. I don't know how to call that, but So we